All right, this is scanning part 2 here. On our last one, we had talked a little bit about using Nessus to do a regular vulnerability scan. Then we did a little proof of concept demo as well. This one we'll talk a little bit more about some other scanning techniques. One of them is with a web application scanner. Now there is a particular one called Nikto in this case here, and Nikto is pretty awesome. It's being used mainly for just your basic web applications and such. So what we're going to do here is take a look and see that we have XAMPP running right here, which is just a free open source web server using Apache, MySQL, and FileZilla. So we have an Apache server running on here. So we'll go ahead and go over here to our Cali, and we're going to type in the word nikto-h, and then the address 10.0.103 in this case, and hit enter. And you'll see here it starts to come up, finding a few different things. So right there we can start seeing, whoa, everything's cranking by pretty fast. So it says up there on the top, Apache 2.2.12 appears to be outdated. Right there. Also you can see that Perl is outdated. We can see that SSL is outdated. So we're starting to see, okay, this application, this web application is obviously pretty vulnerable in this case here. As we scroll up here, we'll notice that there's no anti-click jacking in place. Looks like Perl is outdated. OpenSSL is outdated for sure. PHP is outdated. Basically, this guy's web application is horrid. It's horrible. We don't like it. So all this stuff here, we can see the different alternatives for index found. Looks like it allows attackers to easily brute force file names with some sort of directory buster and that sort of thing. Let's see here. The OpenSSL one is definitely going to be a problem. Vulnerable to buffer overflow there as well. And it gives a bunch of different OS VDB articles, which is the open source vulnerability database. Also down here, we can see that phpMyAdmin is there. So that's probably a big issue that you would come across as well if somebody allows you to log into their phpMyAdmin page. Not a good situation there. Let's see here. Looks like icons. It says here that directory indexing can be found. So all in all, we can see based off of this scan here, a lot of bad things. So the command is nikto-h, and then the IP address that has the actual web server or web application. So it's a great tool to use for scanning. Okay. All right. So that is a vulnerability analyzer for web applications. So let's talk about some things that we need to be knowing for port scanning. One of them is ports, right? Because if we do port scanning and regular just plain and simple scanning, we need to figure out, okay, what are we actually dealing with here? Because if I'm a bad guy or an ethical hacker, one or the other, and I'm trying to go ahead and do some scans into a machine, and I notice that it has port 42 open, I need to know that that's WINS. If it's 53, I need to know it's DNS. Okay, so some common ones you'll find out there is protocol ID numbers for ICMP when you use ping and traceroute. TCP has a protocol ID number of 6, UDP 17, GRE generic route and encapsulation 47, ESP encapsulate and security protocol 50, authentication header 51. These two here are typically used in L2TP VPNs with IPsec, so very common. Some other ports down here, we got our basic 20 and 21 for FTP, SSH 22, Telnet 23. So there's quite a few of them out here. Now this one's interesting one here as well. Port mapper for Linux. Okay, very common one that most people know about. Port 80. Okay, RPC DCOMs 135. SMB for file sharing. These are usually open. One of those three are usually open on a machine. SNMP is a good one to know about. 161 and 162. 162, I believe, is for traps. Those are used in UDP. SOCKS 5 proxies, syslog, Nessus server, SQL server. So it's a good idea to get a hold of all of these different ports and protocols and start learning all the different ones that you actually have out there so that you can be better informed for this. Another thing you have to be familiar with is some basic TCP versus UDP. So some people that I ask about this sort of thing, they kind of get the idea about three-way handshake. They understand that a little bit, but they don't know kind of the details of it. So I want to go over that real quick here. So if you look at a header, TCP header, typically you have what's called a source port, destination port, sequence number, acknowledgement number, But the key one there I want to point out is the flags, because we're going to deal with that here today in our scanning stuff. So the TCP flags, you'll notice the first two, C and E, those are not actually used. They're reserved. After that, you have urge, ACK, push, reset, syn, and fin. So if you're familiar at all with three-way handshake, the idea of it is I have a computer here, and I'm horrible at drawing on these whiteboards with my mouse, so forgive me. So we have computer A and we have computer B over here. Okay. If I want to initiate a communication with B, I would send something that they call a syn packet. And all that basically means is that I take the flag for syn and I set it. I set it to 1, meaning true. In this case, if B is open and ready to respond, it will then send back some information back to me. And it'd probably be easier if I just type this stuff in here. A little bit easier to read. They're going to send back something called a syn ACK, okay, an acknowledgement. So in this case, I then, A, respond back to B with something called an ACK. And what happened to my... Looks like I didn't save that. Okay, there we go there. And ACK. All right. So in this case here, syn first, then syn ACK, and then an ACK packet. Okay, that's making it reliable in this case here. Now, what also happens on this, it's kind of like if you were doing a telephone conversation, because there's some other flags as well, like fin. Whenever I'm finished, I gracefully end the session. And then there's RST, which is basically reset, and that's ungraceful. It just basically cuts the connection cold. So it's kind of like if I were to make a phone conversation with you, and I called up and said, hey, what's up? And that would be basically a syn, me trying to initiate this conversation. And then if you were to respond back to me and say, hey, man, what's going on? And then I say, okay, that's our syn ACK. And then I respond back, hey, can I talk for a minute? Now I've basically set up the call to say, listen, I want to go ahead and talk to you. And everything after that would be basically the data flow. Then when I'm done talking to you and I've said, okay, great talking to you. I'll see you tomorrow. Have a nice day, blah, blah, blah. And I hang up the phone. This is a fin because I did it gracefully. I didn't, I let him know, hey, listen, I'm closing up our conversation here. I'm going to shutting off my phone and blah, 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 and all that kind of stuff. Or I could have just said, hey, you're stupid, and then close the phone. That's rude and not graceful. And that would be an RST kind of situation. Okay. Also, the idea about sequence numbers comes into play as well for these because it's what makes TCP reliable. So, for example, if I were to go ahead and send the syn packet, what the computer will do is it will generate a random number. So I'm going to say 1, 2, 3 as the random sequence number. Okay. Then B will also send back a sequence number randomly generated. And I forgot to mention the sequence number for the first one. So I'll just say 867. That one. Okay. And then B will also have what they call an ACK number. Okay. In this case here, it will be the sequence number plus 1. Then when I send back my ACK packet, the sequence number will be the last ACK number. And the ACK number on this one will be the sequence number from the last one, 867 plus 1, 868. We can kind of see that in real time. Let's take a look here. So we're going to come over here and let's go ahead and run Wireshark real quick here. Wireshark is a packet sniffer, and we're going to go ahead and use this one here to demonstrate. Close that. Open that up there. All right, so we're going to capture on my ETH0. Start that up there. So I know I have a web server running over there on 103, so I think I can just go ahead and netcat over there. So I can say 10.0.0.103, port 80, enter that, Control C, and then come back here, stop the capture. All right, so let's take a look over here real quick. Now, by default, I think they use relative sequence numbers. So let me go with absolute here. I want to change my preference real quick on my Wireshark. So if you want to see them in their absolute sequence number instead of relative, you would basically go to your preferences and come down to TCP. Right there. And you would uncheck relative sequence numbers right there. Okay. All right, and the way my screen is a little bit hard to see, but let me hit apply on that. And OK. And now we got our real sequence numbers. So if you look here under our transmission control protocol, we can see there's our sequence number, 253553141. So let's take a look at the last three digits, 141. So basically, the SYN packet is a randomly generated one from the source going to the destination. Then the destination responds with a SYN-ACK packet. And what this means here is that the flags, I'll scroll down a little bit here, is the flags have a 1 in the ACK and a 1 in the SYN. Okay, so 1 on the SYN and 1 on the ACK. Okay, that means SYN-ACK. There's no SYN-ACK flag. It's just me setting both of those flags, basically. So again, they're going to also randomly generate a number, and this one's going to be a unique number, and you'll see it ends in 832 here. So in this case, if we knew that the sequence number from the first packet, the SYN packet, ended with a 141, then we know that the ACK packet of the next one should end in a 142. So let's take a look. So right here we can see the acknowledgement number does indeed end with a 142. Now, based off the logic that I drew out a few minutes ago, I would now know that this 142 for the next packet, the ACK packet, this will be the sequence number. And then the ACK number of the next packet would be this number plus 1. So 833 would be how the ACK number will end for that next packet. So the sequence number should be 142. The ACK number should end in 833. Let's take a look at the next packet. So here we go, 142, 833, exactly as we had determined it, okay, based off of here. So that's how you can tell whether or not it's reliable, because this is what makes TCP reliable. Because if it's expected, it's basically saying, hey, listen, player, if you want to respond back to me, you need to go ahead and respond back with this sequence number. Okay, so when it did the ACK number from the SYN-ACK right here, and it said 142, it's basically telling computer A, hey, listen, player, give me this number, the sequence number that you're pushing out with your ACK packet. Make sure it ends with a 142. The reason why is if a bad guy randomly sent a packet, in other words, took over the session and sent back a spoofed ACK packet, the computer B can realize, hey, listen, this is out of order. This is not the right packet that I was looking for. Because, again, it's looking for the 142. If it doesn't get it, it knows, hey, this isn't the right one. Right? So TCP is reliable in that manner there to try to protect against certain things like that. UDP, not so much. UDP just says, man, just pump it out. Just get it to me any way that you can. If some of the packets fall, I don't care. So it's good for speed, right? But not necessarily for reliability. So now that we kind of got a basic understanding of some of that and how packets look and how flags are set and things like that, we're going to go ahead and demonstrate a little thing called HPing3. Now, HPing3 has been deprecated and put into Nmap as nping, but I still want to show you some of these commands here because they still work and they still are effective. So HPing3 in this case here, let's do a -H, and then over here, I'm going to go ahead and use this one to actually run my commands from. And then we'll check back here and see what I'm actually typing in. So first thing we want to try to do in this case here is maybe spoof an address. Okay, so I have a port 80 that's over there on 10.00.103. Okay, it's open and running. And I want to spoof an address to that particular port there. How I would do that would be HPing3 -I and give my ETH number. Now, if you're not familiar with the ETH number, you type in ifconfig, and it will tell you right up there what your number is for your interface. Okay. So let's go ahead and do that. We'll say hping3, and it is case sensitive, by the way, in Linux. Keep that in mind. It is case sensitive. Capital I is different than lowercase I. So ETH0, then we'll do a -A, 1.2.3.4, and I'll explain these switches as we after we finish this. So we'll say -P80, -S, -C10. Actually, let's do 15. 10.0.0.103. Okay, I think that's good. So let's take a look here. First off, the -I, we can see based off over here. I can scroll up here. That should be interface right here. Okay. And the other one we had was a -A. That one there is to spoof an address. So you would need to put the -A and then the address that you want to spoof. So we just randomly picked an address. You could have also done --spoof. Okay, either one. Let's see, the -P would stand for destination port, because I think that's, where is it at? Let's see, right here. So the -P is the destination port. The -S would be a base port. Then we see a -S. Like I mentioned, it is case sensitive because you can see the little s is actually base port. The -S is set in a SYN packet. So it sets a SYN flag. Okay. So we're making a SYN packet. The -C stands for count. So how many packets do I want to send? There. And I said I want to send 15 packets, and then here it says the address being 10.0.0.103. So real quick, let me go ahead and start up my Wireshark again. I probably shouldn't have shut it down. Just so you can kind of see the packet of what we're doing here. So let's see, let's capture interfaces, and let's do our ETH0. Start there. All right, cool. So, where are we at here? There it is. So I'm going to go ahead and run that. It's going to run 15 packets, and then it will stop. So you can see here that it has a, let me go ahead and stop the capture. You can see here that each one of them have a source address of 1.2.3.4. Okay, so that is how you spoof an address using hping3. Pretty awesome stuff. Next, you can also do something called a Syn Flood. So what is a Syn Flood? Well, if you think about it, if I had a web server and it was accepting requests for web pages, that means a user would send a SYN packet to my web server saying, hey, player, let me get the contents therein, please. And what it will do is it put that SYN into queue, and then it will send a SYN ACK back to me. And then my computer, would have to respond back with an ACK packet. Once that's done, we've now set up the connection, and I can download the pages and the goodies and whatever's on the web page. So in this case, a Syn Flood would be, imagine if I were to send a SYN packet and the destination address was spoofed. In other words, it doesn't exist. The SYN ACK packet that would come back from the actual server itself, the web server, would go back to a unknown destination, something that doesn't exist. So it's waiting there saying, hey, I need an ACK packet. I can't do anything. I can't get this SYN out of queue until I finish the three-way handshake. So it's sitting there waiting and waiting and waiting, right? Bueller, just waiting for that thing to actually connect. So that's all well and good with one. But imagine me doing that 50,000 times. Okay? Now I've got all these different SYNs in queue, and it's, a web server is, it's not infinite in its capabilities, so it's going to basically say, okay, this is my limit. I can't accept any more SYN packets. Now everybody else that wants, legitimate users that want to access the web page, I basically deny in service to them, which is why they call this a DOS, denial of service. Because I'm saying, hey, players, you guys can't hook into this web page. I'm first. Get in line, players. Get in the back. So that's basically what's going on here. So there are ways around that. You can use things like SYN cookies where it doesn't keep it in queue and it actually goes ahead and only reconstructs it once it actually gets a SYN ACK back and different techniques. Look up Syn cookies for a defense method. It's a good method, but we're going to demonstrate that you can do a Syn Flood with this to a machine. So to do that, you would do hping 3. In this case here, we'll do a -- flood. And we can also go ahead and pick random source addresses. So we can say -- ran -source, and then I'll target port 80 of 10.0.0.103. Okay? So in this case here, if I were to capture that and hit enter, you can see it's in flood mode. I'm going to Control C out of that. Now, after I've done the Control C, it already sent, in that short amount of time, 42,000 packets. That's insane. Can you say bye, bye, bye? Right? So you can see all of these addresses here under source are just completely random source addresses. Still going to the same destination, but all of these are random source addresses. Okay? So that's the idea behind doing a Syn Flood. That's basically what you would do for that. So let's take a look at the help file here. So we can see the -- flood, pretty common sense. Send packets as fast as possible. And then the ran -source, I think, is kind of goes without saying. It has random destination address mode, or I'm sorry, random source addresses. Okay, so that's why we did that one. -P, we already know, is destination port. All right, very cool. Now another one you can do is interesting as well, is if somebody has ICMP blocked, then something of note is that if you were trying to ping a machine to see if it was up and running, if somebody had blocked ICMP, it won't take or receive any echo requests. So in this case, what can you do? Well, it's handy that with hping 3, that the default mode is TCP. So you essentially could just go ahead and do a ping, or hping 3 actually, to the machine. So I could say hping 3, 10.0.0.103, and do it that route. Okay? And that's using TCP. But if I did want to specify, I can specify a mode. So if I wanted to do an ICMP ping, because the default is TCP, I can do hping 3 -I, or I'm sorry, -1, and then the address 10.0.0.103, and it will do a basic echo request. Okay? So notice the differences here between some of these ones here, is we see ICMP sequence here, but on this other one, we're seeing TCP. See the RA, which stands for reset ACK? You don't see those down here, do you? Because this is the ICMP mode being used here. This is the TCP mode being used here. We get the Windows length, we get all that kind of stuff. Pretty awesome stuff. All right. Now, another one you can also do as well is something called an Xmas attack. And this particular attack is, well, it's more of a scan, and we'll see it again in Nmap when we go over some Nmap stuff. But the idea here is that if you have an IDS, intrusion detection system, at the target, a lot of times an IDS will filter for particular flags. For instance, Syn and ACK and Fin, and, well, not usually Fin. It'll usually be like Syn and ACK, because those are your main ones. Because if I do set up a session, it's going to be with one of those two flags, Syn and ACK. So if I'm an IDS and I'm monitoring full connected sessions, I want to monitor for Syn and ACK packets, okay, or those flags. So in this case here, you can do a trick, as it were, and try to scan a machine by only turning on flags that are not really well known or not really well used in a lot of different IDSs or filters, and that would be urge, push, and fin. So specifically for an Xmas attack, we're looking at urge, push, and fin, setting those flags. So to do that, we do hping 3, hping 3 -F -P -U, and I didn't put my dash. There we go, -U. And then we give it an address, 10.0.0.103. Oops, whoa. 103, there we go. And then a port number of 80. Now in this case here, I'm not going to really run this here because it doesn't actually work against Windows. Okay, there are some rules, I guess you could say, that IEEE and some of these other standards have decided that if things happen in TCP and I were to do this one particular thing to this one particular machine, this machine should respond in this particular way. And those are basic rules that are set up that most computing technologies agree with. Unfortunately, Microsoft decides not to play ball on a lot of those, and they basically disregard those particular rules on how they're supposed to respond. And these particular ones don't work on this, like this command here doesn't work on Windows, but it will work against a Linux or Unix because they're following the standard of how it should respond. But anyways, this is what the command would look like, and we can see here that the -F, -P, and -U are to set the fin flag, the push flag, and the urge flag. Now, you could have just done Xmas as well, or -X, and that would have done basically the same thing. Okay? So that's an interesting scan that you can do right there as well. Now, there's another one that doesn't work on Windows, but it's an interesting attack you can do against Unix and Linux, and it's called a Smurf attack. This one's an interesting concept. Let me break it down to you like this. So let's say that I had a computer here, and we're going to call this one the attacker. So A for attacker. And then we have a computer down here. We'll say V for victim. Okay? If I were to go ahead as the attacker and send a ping echo request to a machine that has ICMP enabled, it should respond back to me with an echo reply. All right? That's common sense. What if I did this, though, and I decided to take the source address of this packet here, and I put the actual source address of the victim? So in this case, I've spoofed the address of the victim. So who gets the reply? Well, it ain't going to be me, because the source address is the victim. So therefore, it's kind of a reflect attack where we'll actually go ahead and give the echo request, or I'm sorry, echo reply back to the victim. Now, you're probably thinking, well, that's no big deal. It's just one packet. Would be. Yeah, that's true. It's still, the concept still applies, though, that it's a reflect, right? It's reflecting off into the server onto the victim. Now, let's take that a step further. Let's say that we had a network over here, and this network had, I don't know, let's say 500,000 computers in the network, okay? No subnet. It was a 500,000 computer subnet. In this case here, if I send a broadcast using IP version 4, if I send a packet to the broadcast, who hears it? Well, everybody, right? So if I do the ARP business, it's basically shouting out on the network, who has this address, blah, blah, blah. So anything sent to the broadcast of a network, everybody will hear it. So in this case, what if I did this same attack, and instead of using a computer here, I sent it to the broadcast address of this network? Now, again, I set the source as the victim, so you can kind of see what goes on here. So echo replies, right? I'm sending echo request, actually, to 500,000 computers. If ICMP is turned on, they should respond with 500,000 echo replies. Back to who? Back to me, the attacker? No. Back to the victim. Therefore, kaput. He's done. Okay? Can't handle it. So in this case, this is what they would call a distributed denial of service attack. In this case, again. Now, there's another one that's very similar to this that uses UDP instead of ICMP, and it's called the Fraggle attack. It's apparent that the people that come up with these names are obviously 80s Saturday morning cartoon watchers. Fraggle Rock and Smurf attack and all this other stuff. This one here, the ICMP one, is called a Smurf attack. Okay? So if you ever hear that term, they're talking about a DDoS. So how would I do something like that in Cali? Now, again, this won't work against my Windows machine because, well, Microsoft chooses not to participate in that. So they actually stop anything. I think it's the echo request going to a broadcast. I think that's what they don't allow. So it's a little different there. This works great against Linux and Unix, though. So to do something like this, you would say hping 3. I don't know why I keep saying 4. And then for this one, you'll do a -1 for ICMP mode. And then you'll say flood to flood the packets. And then, of course, we're going to spoof the address. So let's say the victim is at 10.0.0.103, and they're in a /24 network. Okay? If they're in a /24 network, we're looking at a Class C here. So we can say, in this case, 10. Let's see. Let's actually do Let's just do this, just for demonstration. I'll just say 255 at the end there. So 10.0.0.255, because again, if it's Class C, we're dealing with a 4th octet. So I'm basically sending it to the broadcast address of this network. So in this case here, the 103 is the computer that I'm trying to say is the victim, and then the 255 would be the broadcast address. And that's basically how you would do that particular attack. Another one that's interesting as well is called a land attack, where you actually send it to the same, you set the ports, source and destination, as the same port. Now, sometimes that will work against Windows as well. So I'd actually like to see if that will work. I haven't tried it yet, but I think it may work against Windows. Let's try it against this one here. Actually, let's do it instead of this one. Let me close this out here. Instead of doing it on this one, I'm going to do it against my domain controller. Yeah, we'll do it here. Let me bring up command prompt real quick. Actually, let me bring up Task Manager instead. Details. Okay, so the memory is not getting hammered. So 0.6 out of 1 gig, not too bad there. CPU looks like it's at 3%. Oops, now it's jumping up 19%, 18. So it looks like it's kind of fluctuating between 1 and 20. So it's not being hammered. We can see the CPU is good. So let's see if this will actually work against it. But the attack still works the same as far as the address. And so we'll say hping 3, and let's do very verbose information, debug amount of information. And we'll do a count of, let's say, 1, 2, 3, 4, 5, 6, 7. We'll do about 7. Yeah, that's about right. We'll do that. We'll do that amount of packets. Data length 120. We'll say dash capital S is to set a SYN packet. Dash W64 is to set the window length of 64. We'll say the port is 445, and then we'll say the source, both the destination and the source, will be 445. Okay, and this is what they call a land attack. And I will go ahead and flood it. And let's go ahead and use random sources. So ran-source. Okay, and the machine over there is 10.0.0.10. Okay, so we'll do that. We're in flood mode now. Let's go back and check on our server over here. All right, we can see the CPU now is steadily climbing, or it was. All right, so you can see it's kind of tapping out here at 57%. So if we added more counts, more packets to it, it definitely would put it over the edge. So that's pretty awesome how we can crank it. See how we're still maintaining that 62, 54, and oh, now it's up to 70%, steadily climbing. So you can see that the more packets we would add, the more hammering that it would do to that particular machine. Okay, so that is a flood attack that you can do as well. Pretty interesting stuff. But anyways, that's hping 3. It's actually been integrated into Nmap, which is what we're going to talk about in our next module, as nping. So it's a pretty awesome little tool for you guys to use for any type of scanning processes that you want. So in the next module, for the part 3, we'll talk about Nmap, and we'll go over some of the different switches and things that you can use for port scanning with the default tool called Nmap.